Good afternoon. I am Chen Yanping from Southeast University, China, and I am grateful for the opportunity to present the findings of my research. The topic is to examine the impact of nanoplastic on intestinal barrier function through the animal and organoid models. I will elaborate from the following aspects. Firstly, I will introduce the background of the study. Plastics, as one of the most common man-made materials, has been mass-produced and discharged into the environment in recent years, have been mass-produced and discharged into the environment in recent years, and have been decomposed into microplastic and nanoplastic under the action of nature, in which those with dimensions less than 5 millimeters are known as microplastic, and those with dimensions less than 0.1 micrometers are known as nanoplastic, and those that are present in environment accounted for the main body of the polypropylene and polyethylene and polystyrene. A review of the literature reveals the humans are exposure to approximately 0.1 to 5 grams of nano and microplastic per week from a variety of sources, the vast majority of which originate from food and drinking water. Since the first detection of micro and nanoplastic in human feces in 2018, plastic particles have been found in human placenta, blood, lungs, and even breast milk, indicating a growing threat to global public health. The digestive tract serves as the primary mode of exposure to plastic, but toxicity studies on the intestinal are not very clear. The intestinal barrier, however, plays an important role in blocking contaminants and maintaining intestinal homeostasis. Epidemiological studies have found more plastic in the feces of patients with inflammatory bowel disease, and nanoplastic are more likely to penetrate the biological barrier due to their small size. Therefore, this study focused on nanoplastic-induced gut toxicity with emphasis on the barrier function. Due to the limitation of 2D cellular and animal experiments, organoid technology has been rapidly developing in recent years, which has a similar structure and cellular composition to that in vivo and can reproduce key functions. It has been rapidly applied and developed in several fields and has also gained the attention of toxicology researchers. With the gradual banning of animal experiments, organoids will become a new platform for toxicology research. The small intestinal organoid used in this study is one of the most mature organoids, which possesses a highly similar structure and key functions to the real small intestine in vivo, and is an excellent model for studying the impairment of barial function by environment pollutants. Next, I will share the content and results of my study. Firstly, I conducted the nanoplastic toxicity tests at animal level. Mice were exposed to polystyrene nanoparticles by daily gavage for 28 days. The dose was set to refer to the weekly intake of human in the literature, while the low-dose group was close to the lowest value of human intake, and the high-dose group was close to the average value. The experimental results show that the polystyrene nanoparticles significantly reduce small intestinal organ coefficients in mice in a dose-response relationship. Polystyrene also significantly damages intestinal tissue structure, especially villi and crypts, and decrease the number of goblet cells. Additionally, the mice exhibited indications of systemic and intestinal oxidative stress, inflammatory response, and reduction in antioxidant capacity. The subsequent tunnel staining reveals that the polystyrene will induce apoptosis in mouse intestinal cells. Furthermore, the level of lipopolysaccharide, diamyl oxidase, and D-lactate, which serve as permeability markers in serum and intestinal tissues of mice, as well as immunohistochemistry, which assesses the level of 3 proteins that are of particular importance for maintaining the tight junctions between intestinal epithelial cells, demonstrate that polystyrene significantly disrupts the intestinal barrier function in mice. And alexin blue staining revealed a notable decline in mucus coverage and a reduction in the number of goblet cells. In conclusion, the ingestion of polystyrene nanoparticles has been demonstrated to cause damage to the intestinal structures, particularly the villi and the crypts, and to elicit a significant toxic response. Secondly, polystyrene was also found to significantly disrupt intercellular tight junctions, increase intestinal permeability, interfere with mucus secretion, and disrupt normal barrier function. Additionally, an evaluation of nanoplastic toxicity will be conducted using small intestinal organoids. Firstly, the organoids was generated in vitro and observed and recorded under a light microscope for 7 days, which showed that the organoids were well-grown, proliferated, budding, and presented a similar structure to intestines in vivo. Subsequently, the organoids was fully characterized, and hemotoxylin eosin staining shows that the intestinal organoids has a complete crypt-villal structure. Immunofluorescence staining for gut-specific markers shows that the organoids had the same cellular composition as the small intestinal in vivo. The above data confirm that in vitro construct small intestinal organoid maintains the morphologically and functionally mature small intestinal phenotype and can be used for subsequent toxicity study. We conducted toxicity tests using small intestinal organoids, and the results show that the morphology of small intestinal organoids was altered by polystyrene exposure, with the darkening of the color, blurring of structure, and inhibition of the budding process, as well as reduced the organoid activity and reactive oxygen species, and the apoptosis level was increased. Small molecular permeation assay shows that the polystyrene significantly increased the permeability of intestinal organoids at a high dose. And immunofluorescence shows that the expression of tight junction protein 01 decreased and the lattice structure was disrupted. The same results was seen in occluding and clotting proteins. Valine proteins expression was also decreased. And the mucin expression signaled that polystyrene altered the mucus secretion and damaged the gallbladder cells. A short summary of the above findings. Firstly, we successfully generated a small intestinal organoid in vitro, and the organoid has a similar structure and key functions to the real small intestine. Second, nanoplastic can significantly disrupt the morphology and structure of organoids and induce a series of toxic reactions. And more importantly, disrupt the intestinal barrier function. Finally, the present study is summarized and reflect upon. For the stimulation of environmental pollutants nanoplastic, intestinal organoids show constant response with those in vivo and have more advantage. And with the gradual maturation and standardization of organoid technology, there is a high probability that organoids will replace animals as a new model for toxicology studies. This is all I have shared. Thank you to all members of my team and the support of the National Nature Science Foundation of China. Thank you for listening.